Mm-hmm.
Hello everyone, I hope you're doing well. In this video, I'm going to find out what the second order eigenvalue for nth state of linear harmonic oscillator under the cubic perturbation. This is a requested video and we have already calculated the first order and second order energy corrections, and in this video we are going to calculate the second order wave function correction. And let's see how we can do that. First of all, we should know the formula that we are going to use. We know that, and keep that in mind, that the system of linear harmonic oscillator is non-degenerate in nature. Okay, its energies are non-degenerate. That is why we'll be using the non-degenerate perturbation theory. All right, so we know that the formula for second order, for calculating second order wave function correction, is given by, so let's write down the formula. It's psi with nth state, because it's calculated for the nth state, so we'll write the state in the subscript and the order in superscript. So we'll be writing it like that. It's second order wave function correction for the nth state. That is equals to, now we'll be having multiple terms, so multiple terms alert. It's summation k is not equals to n, then we have this bracket, then summation again, m is not equals to n, this summation is k is not equals to n, and this summation is m is not equals to n. We have this bracket and this summation, another summation inside, h m n prime. This is a Hamiltonian. We'll see what these are equals to. Okay, we'll understand them later. Let's write down the formula first. En of 0 minus em of 0 bracket, then we have En of 0 minus Ek of 0 bracket, then we have that negative sign and we have another term. This is one term and we have another term, so it's h n prime h j n prime divided by En of 0 minus Ek of 0 and its whole square of it, and we have this bracket, that bracket closes, into psi k of 0. Well, this is the formula in its full glory. You can see there are two different terms in here, and don't be scared if you can see the whole, a lot of terms. They will reduce into fewer terms later depending upon the Hamiltonian that we have. And let's see what does each term represent here. We can see these are the energies, and these are zeroth order energies for the nth state, and they are really easy to calculate. For example, we know that En of 0 is simply equals to n plus 1 by 2 h get omega. Just replacing n by m and k, you can easily find out the energy for any state that is given to you. So that's really easy to calculate, and we'll insert it after opening up these summations. So we don't need to do it right now. We'll be doing it later on in the video. And we first need to calculate these Hamiltonians, and they are really important. So you can see there are 4 different Hamiltonians. Let's see what they are equals to, because they are in symbolic form here, and they can be written in the form of scalar product, and that scalar product needs to be calculated for this calculation to be completed. So let's see what they are equals to, and then we can proceed with the solution. We can see we have 4 different Hamiltonians here. Let's see what they are equals to. They're all scalar products, and they are the scalar product of psi with Hamiltonian and then psi again. This is a common thing among all of these products. They'll be written like that. We have psi first in the bra section, then we have h prime, then we have psi, as this is the operator that is applied on this ket. And there is another thing that is common. They're all zeroth order wave functions. You can only write this term, this symbolic term, for zeroth order wave functions, not for the first order, second order, and so on. All right, you can only write them for the zeroth order. That is another thing that is common among all of these things and all of these expressions. Now you'll first write m as state of first wave function and n as state of second wave function, depending upon the order they are written in. So k first, then m, n first, then n again. They are both n. It's k first and then n. Okay, simple as that. It was really simple to do, and we can also write them in another expression, like only writing the quantum numbers these days. Like we can write m instead of this whole thing. We can only write m, then h prime, then n. Similarly, we can write k, h prime, then m. This notation is really important and easy to handle when we are dealing with ladder operators, and we'll be using ladder operators to calculate everything involved in here. So that is why I'm writing it in this form: k, h prime, n. All right, and first of all, I'm gonna calculate this one because it doesn't involve any summation. You can see that k, m, and k, so they all involve some kind of summation to solve, but this one could be solved really quick, and let's do that and you'll see why I'm saying that. And h and n prime, that is equals to n, h prime, then n again, and we have the perturbation. Let's put that perturbation in here, ax cube. We can take a outside because it's constant, and x cube n. We can see here that this forms a odd product. This is an odd scalar product. It's because it's n wave function, this is n wave function. Product of two similar wave function makes a even function. Okay, and they both combine to form a even function. Then we have this odd function x cube. This is odd, and we can see there is a product of this term and this term, so it's even multiply odd, which is always odd, hence this whole term makes up a odd product. And the integration of odd product over whole space is always 0, and we can see that the scalar product means that the integration is done over whole space, hence this odd product becomes 0 since the scalar product is odd. Alright, so we can see that this term is 0, and if you refer back to this expression, you can see that this is the term we were talking about, and it's equals to 0, and it multiplies with all of these quantities. It's like 0 multiply this whole quantity, which makes whole term 0, and we have this term right out of the scene, and we have only this term to solve in order to calculate the second order eigenvalue. And we have a simpler case right now. You can see that we have reduced the number of terms, and now we need to calculate hmn prime and hkm prime, these two terms only. Okay, we don't need to calculate this one as well because this is 0, it makes the whole quantity 0. So that is a good thing that happened to us. Let's calculate hmn prime and hkm prime, and there is a good news that you can see they only differ by quantum states. Rest of everything is same, so we can calculate one of them and we can shift the quantum numbers to see what this would be equals to. Okay, so let's calculate hmn prime. Now let's calculate this one, as we already know that this is actually equals to m quantum number, then h prime Hamiltonian, then the last quantum number, that is n. Alright, so this is what we need to calculate, and we can put the value of h prime here. So we have ax cube. You can put hat over them to show that they are operators, and since a is a constant, we can take it outside and it's simply this. Alright, and this is something that we need to calculate. Let me call it as equation number, let's say it's a. Now here I'm going to calculate this part first, where this operator is applied on n ket, and for that purpose I'm going to write it here. I'm just doing it so that we have some simplified form, and we just don't need to write these things, surplus things, repetitively.
because they are not gonna be solved until we calculate this one part. So let's calculate this one part first, and for that purpose I'm gonna let that this position operator is equals to, let that is equals to h cut by 2m omega whole power 1 by 2 a plus a. This is the lowering operator and this is the raising operator. Okay, I'm expressing the position operator of linear harmonic oscillator in terms of raising and lowering operator. These are actually the ladder operators. So whenever we have these nth states or some general states involved, we have to use the ladder operators or some alternate method to calculate all of these things, because like these integrals, because we can't do it otherwise using those integration things, because that makes it really complicated and almost impossible to calculate. Okay, so let's see that since it's x hat, this is only x, we need x cube, so we can take cube on both sides, taking cube on both sides. Since it becomes x cube, that is equals to h cut by 2m omega 3 by 2 a plus whole cube. All right, so we have this situation right now. Now we need to calculate this thing, because that is something that is new to us. This is a constant and these are operators. Let's open this cube and see what this is equals to, and then we can apply this thing right here to calculate this. So let's do that. A plus whole cube, that is actually equals to a plus times a plus times a plus. You cannot use those mathematical formulas where, you know, a cube plus cube plus 3a cube. No, you can't do that. You have to multiply them separately, because in operators the order matters and in simple scalars the order doesn't matter, and that is why you cannot use those mathematical formulas. Let's do that here. First, I'm going to multiply these two together, and I'll multiply a with this digit and then with this. So first a and then a, then a with a plus. Next, I'm going to multiply this a plus with this a plus with a plus. So this is it, and that one as it is. Next, we will multiply this one with these two one by one. We'll multiply all these numbers with these two one by one. So a and a plus a plus plus, then we are going to multiply this one with both of these, so it's a plus then a. Order matters, keep that in mind. We'll have this one first and then this one, a plus a plus. Next, we are going to multiply a plus a with these two, so it's a plus a plus a plus plus, now it's the last term, it's a plus a plus a plus a plus a plus a plus. Okay, so that is what this cube is equals to. Now let's put this value into this expression, and we'll then have this situation. Hence x cube is simply equals to, or we can write this cut as well on the right hand side, h cut by 2m omega whole power 3 by 2. Then we can write all of these operators in a bracket, a plus a plus all of these values. Okay, let me write it. Well, I have written all of these values in this bracket, and at the end we'll have that cut on the right hand side. Next we have to multiply this cut inside, so that this cut will appear on the right hand side of each of these operators, and let's do that in next step. X cube n cut, that is equals to h cut by 2m omega 3 by 2, and then we'll start the bracket and we'll write all of these terms with a cut on their right hand side, okay, like here. So we'll do that for all of these terms. There are a total of 8 terms in here, so you can count them to ensure that you haven't missed any, because that's the kind of mistake that most of the students do when they have multiple terms involved. A plus A plus plus A plus AA plus A plus AA plus plus A plus A plus A, and the last term, that is A plus A plus A plus, bracket closes. All right, so we have 8 of these terms, 1 2 3 4 5 6 7 8. We need to calculate all of these terms individually, and we'll put those values right back into this expression. I'm going to call it as equation number B. Okay, so let's calculate all of these separately and see what it is equals to, and then we can put all of these values right back into this expression. For that purpose, we know that we'll write down these important formulas that will guide us to how to calculate each of these terms. So we have, when the lowering operator applies on a ket, let's say the ket is some p. Okay, I'm using a different quantum number because they could be any. I'm not writing this specific, so that you'll see the ket will change when we keep on applying the operators. So for a general ket p, when a lowering operator applies on it, then what happens is that we have the ket reduces by one number, okay, multiplied by a constant digit, which is under root of this what was in the ket. Okay, just the ket changes by one digit and multiplied by under root of this thing. Okay, this is what happens when we apply the lowering operator on a ket. When we apply a raising operator on a ket, then what happens is that we have this state raised by 1, the ket raises by 1, and it multiplies with a constant that is the similar. Okay, we have similar thing, the raise in the value under root as constant also in ket, but in lowering operator we just have under root p, but the state reduces by 1, as we can expect from a lowering operator. So using these two formulas we can find out that what these things are equals to. Let's do that one by one for each of these terms and see how we can do that and what they are equals to. So this is the first term, and we'll apply the operators one by one. A remains as it is. A is applied on ket. This is the first thing that we'll do, and you can see the lowering operator is applied on a n ket. So wherever there is p in this formula, you need to put the value that is inside this ket. Okay, just apply the formula compare, and you just need to put p equals to n, because you can see on comparison that here it's p and here it's n. Just put n in these places of p, so you'll get the value. It's under root n and n minus 1 as ket. All right, since under root n is a constant, we can write it outside, and we have a, and now this a operator will apply on this ket, so it's a into this ket. You can see the ket has been changed. Now you can see the lowering operator is applied on this ket and lowering operator is applied on ket. So you need to put p equals n minus 1. Wherever there is p, just put n minus 1 and see what it equals to. Okay, and let's do that. Under root n a. So here under root, instead of p you'll write n minus 1. Then this ket, instead of p you'll write n minus 1, and this minus 1 was already there, so that is how it comes out. This under root n minus 1 is constant, so we can write it outside. A, n minus 1 minus 1, minus 1 minus 1 is minus 2, so n minus 2. This is the new ket, and now we can see another loading operator is applied. So the same thing will happen. Instead of, here you can compare, here in place of p we have n minus 2. Wherever there is p, put n minus 2. So it's under root n minus 2 in cat n minus 2 minus 1, which was already there. So yeah, you can write all of these in a single under root because they are all under roots. So you can write them in a single under root, and it's n minus 3 cat. In that way, we have calculated this term. Now the second term is a plus cat. Once we are comfortable with applying these cats, I'll speed up the process because there are many terms that we need to calculate. And let's apply the operator a. This is the closest to the cat, so we'll apply a plus first. A plus applied on n cat. A, and you can see that raising operator is applied on n, so we'll use this one formula, and instead of p you'll write n. Okay, you just need to compare what you have. Okay, and we can see that instead of p it's n, so you'll put n in place of p here and you'll get the result. So it's n plus 1 and cat is n plus 1. All right, now this under root n plus 1 could be taken outside because it's a constant. A and a will be applied on the cat. Operators only applies on cats, that is why we just keep the constants outside. And under root n plus 1, now a, we'll apply this a on this cat, so what you are gonna get. And loading operator formula alert, this is the one that we are going to use. So instead of p we have n plus 1 here in the cat, so instead of p you'll write n plus 1 wherever there is p. So it's under root n plus 1 and n plus 1 minus 1. N plus 1 is p, minus 1 is already there, and n plus 1, and this is also constant, and you can see both of these are same, so we can write whole square of it. A, this constant is under root n plus 1, and this is also under root n plus 1, so we can write the whole square of it. And here n plus 1 and minus 1 cancels out, and it's n only that is left. Next, it's n plus 1 simply because square and under root cancels out. A applied on n, the lowering operator. So we know that when a lowering operator applies on a cat, what happens, it's a constant of same quantum number and the cat reduces by 1. You can remember this rule. Okay, for lowering operator it's constant of quantum number and quantum number reduced by 1 in cat. All right, while for a raising operator it's constant raised by 1 and cat raised by 1. That's the simple formula, and you can find out the values to any of these. So this is the final result for the second term. Now let's do it for the third term. This is the third term, a plus, and a is applied on n. So a plus, lowering operator applied on a cat, so it's constant of the same quantum number and cat is reduced by 1. Under root n remains the same. A plus now will be applied on n minus 1. This one will be applied on n minus 1, and we'll use the same rule. What will happen is that we'll have under root of this number plus 1 and cat of this number plus 1. That method is easier and quicker. So minus 1 plus 1 cancels out, it's under root n, and here the same thing happens, it's cat n. We can take under root n outside, so it's under root n whole square. A applied on this cat, square under root cancels and it's n. Lowering operator applied on cat, so it's under root n and cat is reduced by 1. Okay, that is the third term. Now let's do the fourth term, which is a plus cat. First, the raising operator will be applied on a cat, and for raising operator quantum number increases by 1 in constant and also in cat. Then under root n plus 1, a plus applied on n plus 1, this one a plus. Now let's apply a plus now. Constant is n plus 1 raised by 1 also get raised by 1. It's under root n plus 1, and it's under root n plus 2. Plus 1 is n plus 2, so I'm gonna take it outside already, and it's n plus 2 here, a, and here n plus 2 as well. Next we have under root n plus 1, under root n plus 2. Then we have this lowering operator applied on a ket, so it's under root of same quantum number, and ket is reduced by 1. N plus, and you can see it's under root n plus 2, under root n plus 2, so it's simply n plus 2 as a result, because square and under root cancels out. And we have n plus 1 here because it's plus 2 minus 1, which is actually plus 1, and that is the fourth term. Let's calculate the fifth term, a plus a plus a. Then we have this lowering operator applied on a ket, so it's under root of same quantum number, and quantum number reduced by 1. A plus, okay, so it's under root n here, a plus a into this ket. Under root n, a plus lowering operator again applied on this ket, so it's under root of same quantum number, and quantum number reduced by 1, so it's n minus 1 minus 1, under root of n into n minus 1. You can write it under the same under root. Okay, so it's a plus now applied on n minus 2, minus 1 is, so it's under root n into n minus 1. Now the raising operator is applied on this, so it's under root of n minus 2 plus 1 and n minus 2 plus 1 raised by 1. Okay, so under root of n into n minus 1, and under root of minus 2 plus 1 is minus 1, so it's minus 1 under root, and here as well. And you can see that it's under root n minus 1 here, under root n minus 1 here as well, so the under root cancels out, and we have n minus 1 without the under root, and under root of n only, and n minus 1. And this is the fifth term. Now let's calculate the sixth term. Here is the sixth term, a plus a plus will be applied on a ket, so raising operator, under root of quantum number increased by 1, and also on the ket. We have under root of n plus 1, a plus, now the lowering operator will be applied on n plus 1. It's under root n plus 1, a plus, now the lowering operator applied on this ket, so under root of same quantum number, and ket reduced by 1. It's under root n plus 1 whole square, since you can see the same quantity, so a plus will be applied on this ket, plus 1 minus 1 cancels out, and it's n ket only, square under root cancels out, n plus 1, raising operator applied, so it's n plus 1 quantum number raised by 1, and also ket raised by 1, and it's n plus 1. It's the final result. Okay, this is the final result for the sixth term. Now let's write the seventh term, a plus a, that is equals to a plus lowering operator is applied on ket, so it's under root of same quantum number, and this it's lowered by 1, so a under root n into a plus. Now a plus will be applied on n minus 1, under root n, a plus, here n minus 1, so raising operator, n minus 1 plus 1 in constant, also n minus 1 plus 1 in ket. Minus 1 plus 1 cancels out, and it's simply under root n, and this is under root n, and this is under root n, so it's under root n whole square, a plus on n ket. Square under root cancels out, n into raising operator applied on ket, raised by 1, yeah, that is it. Now the last term, congratulations, it's a plus applied on ket. Let's do that one by one. A plus applied on ket, so it's under root raised by 1, ket raised by 1. Then under root n plus 1 outside, a plus, this a plus applied on n plus 1. Under root n plus 1, a plus, ket raised by 1, sorry, constant raised by 1 and ket raised by 1 as well. it's n plus 2, so we'll write n plus 1 into n plus 2 here, a plus into n plus 2 ket, n plus 1, n plus 2, a plus applied on n plus 2, so it's under root of ket raised by 1 and constant raised by 1. It's under root n plus 3, so we'll write n plus 1 into n plus 2 into n plus 3, and here we have n plus 3 as the final ket. In that way, we have successfully calculated all 8 of these terms. Let's put all of these values into this expression number b, equation number b. Okay, let's put all of these values here, and then we can simplify. So we have h cut by 2m omega whole power 3 by 2. Now let's put all these values one by one. First is this term, so that is equals to this, so let's put it right here. It's under root n into n minus 1 into n minus 2, and ket is n minus 3, plus second term, which was this one, it's n plus 1 under root n minus 1 is the ket, plus the third term, which is this. Let's put in here n under root n minus 1 is the ket. Then the plus sign, fourth term, which is this, and under root n plus 1 under root, oh sorry, n plus 2 only, and ket is n plus 1, plus the fifth term, which is this, it's n minus 1 into under root n minus 1 is the ket, plus the sixth term, which is n plus 1 under root n plus 1 plus 1 is the ket. Okay, then plus seventh term, n under root n plus 1, ket is n plus 1, plus the last term of the series, which is under root n plus 1, n plus 2, n plus 3, and it's multiplied by its ket, which is n plus 3. Okay, and we'll close this bracket. So we have all these terms in here, and we can figure out, like, we have some common kets. All right, this is n minus 1 ket, this is n minus 1 ket, this is n minus 1 ket. Similarly, we have n plus 1 ket, n plus 1 ket, and this is n plus 1 ket as well. And n minus 3 is unique, n plus 3 is unique as well. So let's make the other ones unique as well by taking common and simplifying and see what we can, get into. Always do this thing, always simplify first, and then we can proceed with opening up the summations, because you have to simplify them firsthand. And let's do that. X cube n, that is equals to h cut by 2m omega 3 by 2. Then the bracket starts, and I'm gonna write this term and these unique terms first, because they doesn't need to be simplified. And it's under root n minus 1, n into n minus 1, n minus 2, ket is n minus 3. Second, I'm gonna write this one term, so it's plus under root n plus 1, n plus 2, and n plus 3, and its ket is n plus 3. Rest of all of the terms requires simplification, so we will be writing them now. Okay, what I'm gonna do is, first, we always write kets on the right hand side, so it's a thing that we need to do. And let me make it clear to you people in rough work so that I can write directly here. And I'm gonna consider these n minus 1 kets. You can see that in these n minus 1 kets, under root n is also common. Okay, so we'll take under root n, this is under root n, under root n, under root 10 in all of these terms. So under root n, n minus 1 ket, we'll take both of these quantities as common, and we'll be left with n plus 1 for this term, n for this term, and n minus 1 for this term, and they'll be added to each other. So let's write them down here. we'll write n plus 1 only because these two will be taken as common. Okay, so it's n plus 1 only. Then here we'll have n only because both of these are common, so plus n. Then in this term we have these two as common, so it's n minus 1 only, so plus n minus 1, bracket closes, and then we are gonna write under root n and n minus 1 get something that we took as common. Now let's talk about the n plus 1 gets. So we can see in n plus 1 gets, n under root n plus 1 is common, and if this is n plus 1 cat n under root n plus 1, and here as well you can see. Okay, we'll write these constants only that is left behind. So it's n plus 2, you can write them down in brackets. So it's n plus 2 for this quantity, then n plus 1 for this quantity, plus n plus 1, plus n for this quantity, bracket closes, and then we have under root n plus 1 into n plus 1 cat, under root n plus 1 and n plus 1 cat. Okay, so let's add them together, these inner terms, and see which we are gonna get. So this bracket closes up here. Let's do this last summation. So it's x cube on n, that is equals to h cut by 2m omega 3 by 2, and bracket starts this one bracket. Then we have these terms as it is, n into n minus 1 and n minus 2, cat is n minus 3, plus this whole under root n plus 1 into n plus 2 into n plus 3, and n plus 3 is the cat, plus now this simplification, we can see here that this plus 1 and this minus 1 cancels out, n plus n, which is 3n, we can write 3n outside. We have under root n, and the cat is n minus 1 simply. Then we have, you can see, n, which is 3n, and 2 plus 1, which is 3. So we have in bracket 3n plus 3. We'll use the bracket because we have now two quantities instead of one. Here we only had one term, so we don't need to add the bracket, but here we need to do that because we have two terms. And 3n plus 3 is multiplied by under root n plus 1 into n plus 1 as the cat, and this bracket closes. Okay, this is the most simplified form that we can get for this expression. We have successfully got this expression, and let's put this expression right back into equation number a to calculate this thing. Okay, let's do that. So h m n prime is actually equals to, we had a m x cube n. Okay, and simple as that, we will just write down the expression that we have got into this thing, and it's a, the bra vector, and we will multiply this bra vector with each of these terms. Okay, we'll write down this bra vector with each of these terms. Well, now we have this bra vector, so what we are gonna do is to write down this bra vector on the left hand side of each of these gets. Okay, directly we'll write it on the right hand side of each of these gets like that. So that is what we are gonna do. So I'm gonna write the constants outside directly. It's a as already there. Then we had these h cut by 2m omega 3 by 2. This is the constant here, so I'm gonna write it outside. And then we have all these terms inside, that is under root n into n minus 1 into n minus 2. With this cat, we'll write the bra vector on the left hand side, so it's m first, then the similar line, then we have n minus 3. Okay, you don't need to write this line again because they are just multiplied and this line becomes common. Okay, we only write the one line. So the same happens with every cat. We'll have a bra vector multiplied with each of these cats. Here again we'll write the bra vector first, then n plus 3 as the cat vector, plus 3n under root n, bra vector first, then n minus 1, plus 3n plus 3 under root n plus 1, bra vector first, and then n plus 1. And we have this closed situation, and in that way we have calculated HMN prime. Let me call it as equation number C. So we have calculated this Hamiltonian. Now we need to calculate another Hamiltonian that we were talking about, and we just need to replace some, quantum numbers only, and we can use this expression to calculate the other one as well. We don't need to do that lengthy calculation all over again. Don't need to do that, because there is only difference in quantum numbers between these two Hamiltonians. You can see here the only difference is that we have k and m here, while we had m and n here. So only a quantum number has changed, and we will just replace the expression that we have got for this. Like instead of m in quantum numbers, like in bra vector, this m is mass. Keep that in mind, this is mass. In quantum numbers, wherever there is m, you need to write k, because in place of m we have k here, so we write k everywhere. And for m, wherever there is n, you can see here n is replaced by m. So wherever there is n, you will write m. Okay, you got it? Let's do that and see what it is equals to, because it's only the shifting of quantum numbers, nothing else changes. The formula is still same. We had the quantum number k, then h prime, then quantum number m. And if we put the value of h prime, that is actually ax cube, the same thing. A comes out and we have k x cube and m. Okay, and from C we can write, because we can see that they are similar, so h prime k m, that is actually equals to, let's do the substitution. Okay, instead of here you'll write k. I'm marking it with red wherever you need to write k. Okay, here it is m, here k, here k as well. And wherever there is n, you are supposed to write m. Okay, I hope you got my reasoning behind doing that, because we can see in comparison that how quantum numbers are different in both situations. Okay, rest of everything is same and nothing else changes. So we have this thing constant first. Let me write it down. A h cut by 2m omega whole power 3 by 2. This is mass, this is not quantum number, keep that in mind. I'm telling you again and again. So here instead of n, you're supposed to write m. In here we are supposed to write k and minus 3 plus, then under root n plus 1, sorry, m plus 1, m plus 2, m plus 3, then we have k and, oh sorry, here as well we are supposed to write m. Pardon me, it's m plus 3. All right, now the third term, which is this 3m under root m k m minus 1 plus the last term, which is 3m plus 3 under root m plus 1, the cat bra, which is this k m plus 1, and that is how the bracket closes. And this is the expression for the second Hamiltonian, and we have got the expression for both of these Hamiltonians in that way. That is equation number D. Now let's see how we can simplify this one thing. Let's do that.